we want to now look at the general rules for differentiating calculus. But before we do that, a reminder of the laws of indices. If the base is the same, which is what's happening here, we add the powers. If the base is the same and we've got one divided by another, we subtract the powers. If I've got one power, x to the power a, and then all raised to another power, I multiply the powers. And then the two important ones, which is why I wanted to look at these now, because they apply particularly to the general rules. If I've got a root, the eighth root, so square root, cube root, fourth root, fifth root, and so on, the number that's on the outside is the root. So, for example, the cubed root of x raised to another power, x squared, x cubed, x to the 4, or whatever, can be written as x to the fractional power. The numerator in the fraction, the top number in the fraction, is the power of x, and the root is the denominator. Roots go underneath the ground. So if we want to differentiate a root, a function with a root inside it, we rewrite it in this form to differentiate it. The other one that's worth remembering is that the inverse function, 1 over x to the power something, is written as a negative power. So again, if we want to differentiate some function with an inverse, so the function's underneath, then we bring it to the top and call it a negative power and differentiate that using the general rule of calculus. So those two in particular are very useful. So let's have a look at these general rules for differential calculus. Okay, so the general rules for differential calculus. So on the left-hand side, we've got the function. On the right-hand side, we've got the differential of the function. Using this notation, the prime notation, the differential. Remember, this differential function tells us the rate of change of the original function. So it's a new function which tells us how the original one changes with time or with x. So the most general rule is some number a, x to the n. So x is the variable, and it's multiplied by some constant a and raised to some power n. The rule couldn't be simpler. We just bring the power n down and multiply it by the number in front, so an. And then we take 1 off the power, x to the n minus 1. And if you look at the chapter on differential calculus on differentiating from first principles, that looks quite complicated, and it is quite a long-winded process to go through. But luckily for us, the end result is actually a very straightforward rule. So once we've done it from first principles, we don't bother to do it from first principles anymore. We just apply the rule, and that's what we're going to do. Okay? For example, 5x to the power 3 would become, bringing the power down, 5 3s are 15, x to the power 2. Take 1 off to the power. And I've differentiated it. Simple as that. Okay, so that's the sort of general function ax to the n. Another function that might be worth looking at is the sine function, a sine bx. So some sort of sine function with a constant in front of it, which would be the amplitude, say, and then some little constant b inside, which might be the angular velocity if this was time, omega t. Well, what we do when we differentiate this is, again, we bring the b outside, so a multiplied by b, and then the sign changes to a cosine, and the rest stays the same. So AB cos BX. So just remember the rule. In an exam situation, you'd be given this table of differentials, so you don't need to remember it, but once you've done enough of them, you do remember them. For example, 5 sine 2x. So we bring the 2 out, multiply it by the number in front. 5 times 2 is 10. The sign changes to a cosine, and the rest stays the same. So again, very straightforward. After the sine function, we look at the cosine function. A cos bx. Only one difference, the cosine changes to a sine, but now it becomes negative. Negative AB sine bx. So, for example, 6 cos 3x. Bring the 3 outside, multiply it by the 6 to get 18. Becomes negative 18 sine 3x. So one or two special functions now. The first function is going to be the exponential function. So a e to the kx similar to the first one, the k comes down and multiplies by the a, so ak e, and now the power remains unchanged actually, ax. So this exponential function, where the base of this exponential function is the natural number e, is a very special function. The differential is itself effectively. If we take the special case of e to the x, the differential of that is still just e to the x. It's its own differential. And that's the only function that's like that. Another function that is worth thinking about is the log function. So we've got that the differential of the log x, the natural log of x, is 1 over x. So if I actually think of an example like 3 log x, actually let's change this slightly, logarithm of ax, sorry Alex, it turns out that actually that, so for example this, turns out to be just 3, so the constant that's in front stays there, times 1 over x, or just 3 over x. So any number, that's why I wanted to put it in, Alex, any number inside here, the a here, actually just disappears, it just becomes over x. So if there's a number in front, like the 3 there, then that stays on top, but you divide it then by the x. So 3 log 2x becomes 3 over x, because the differential of log ax is 1 over x. Just over x, yeah. Okay, so if we leave space here on this table, then there may be other functions that we'll come across later on, like the tangent function and so on. So there are other standard differentials that we might well want to put in at some point. But as a start point, this will be enough. So this table of differentials, this table of rules, tells us how to differentiate a function to get the differential, which tells us the rate of change of the original function. Each one of these is a new function. It's not the same as this, it's the differential of it. It's a new function. It doesn't tell us the value of the original function, it tells us the rate of change of the original function, a different thing. So now we need to have a look at some examples of applying these rules, and I'll do those in a separate video.